Okay, so a central topic in this stuff is vector spaces, or as we'll call them, linear spaces. So let's go through a few definitions. No real theorems in this section. But when we say linear space, we mean what you've traditionally called a vector space. So we'll need the scalars to come from somewhere. In the most general setting, we take the scalars to be from some field, maybe a field F. For our purposes, probably more often than not, the scalars will be real, though we'll play up complex scalars a bit more in here than you probably did in sophomore linear algebra. That being said, let's talk very briefly complex numbers. Complex number z will denote as x plus iy, where x and y are both real. I squared equals -1. We'll define the real part of z as the x piece. The imaginary part of z is the y piece. Notice the real and imaginary parts, a little ironically, they're both real. The imaginary parts is a real number itself. So when we deal with real and imaginary parts, both parts are real. When we deal with a complex number, there's the imaginary unit appears before the imaginary part. The conjugate of complex number z equals x plus iy is complex number z bar equals x minus iy. So we simply change the sign of the imaginary part. The modulus, or absolute value, both terms used commonly. I prefer the term modulus myself. My thing is complex analysis, though the term absolute value is used with good cause fairly commonly as well. So the absolute value or modulus of z, mod z is how I'll read this, is the square root of z times z conjugate. So a reason for introducing the conjugate right there. And if we'll multiply z and z conjugate together, we get x squared plus y squared. So we get x squared plus y squared square root of for the modulus of z equals x plus iy. We can verify using series that e to the I theta equals cosine theta plus I sine theta, Euler's formula, for any real theta. You might even see this brought up in a calculus class. It'll be mentioned probably as one of the high-numbered questions in a section on series. And all you do is you take the series for the exponential function, the series for the cosine function, the series for the sine function, and liberally rearrange things, and you'll see that this equality holds. Now that liberal rearranging involves moving around an infinite number of terms, and you better be careful doing that kind of thing unless you have an absolutely convergent series. And these are absolutely convergent series. Even then in calculus, it's a little stretch of the imagination because the complex numbers are playing a role. But these are all absolutely convergent series, and similar results hold in the complex setting. So this is a valid formula. We can also express complex numbers in so-called polar form. Expressing z is the modulus of z e to the I theta. So mod z is playing the role of a radius, kind of an r theta polar representation. And the angle theta, when this is defined, will satisfy tangent of theta equals y over x, imaginary part divided by real part. Of course, when the real part is 0, then we got some problems with this little relationship here. Though for purely imaginary numbers, those for which the real part is 0, we can certainly talk about this theta parameter. Sometimes it's called an argument or the principal argument, depending on definitional preferences. Of course, with polar coordinates, there's an ambiguity as to what the theta parameter is, an ambiguity by a factor of multiple of 2 pi. All right, so we will deal with complex numbers as scalars. We're going to define a linear space, and we're going to define it over a field. So this definition is all-encompassing. Good if you want to use real scalars, good if you want to use complex scalars, good if you want to use scalars from some other field. What other fields do you know? Integers mod p form finite fields. These are some examples of finite fields. So those are on the table as well. We won't really explore that in here, and here the scalars will be real or complex. But for a general definition, we'll define a linear space over field F as a set, capital X, endowed with the operations of addition and scalar multiplication of elements of X by elements of the field, which, for all X and Y vectors and all alpha scalars, we have vector X plus vector Y is an element of set X, and alpha, scalar alpha times vector X is also a vector in set X. So we'll call the elements of X vectors, the elements of F, of course, are called scalars, and we require the following for all X and Y and all scalars. Vector X plus vector Y equals vector Y plus vector X. That is, we have commutativity of vector addition. We have associativity of vector addition as well. X plus Y plus Z equals X plus Y plus Z. It's hard to verbalize, but is indicated symbolically there, where X, Y, and Z are vectors. There is a 0 in X. We'll talk about this a little bit more later, but that's the 0 vector. You know it's a vector because it's in set X, and set X is the place where the vectors are. So there's a 0 vector such that X plus 0 equals X. This holding, again, for all X, as stated upstairs. Of course, this would be the additive identity vector. For every vector X, there's a negative X, a vector which we denote negative X, such that X plus negative X equals a 0 vector. Context tells us we're talking all vectors here. You know, X is a vector. You know, negative X is a vector. We're dealing with vector addition. So we must be dealing with the 0 vector here, not the 0 scalar here. Next, sometimes this is called preservation of scale. If you take 1, the scalar 1, that is the multiplicative identity in the field, that scalar times any vector equals the vector itself. This holding for all X vectors, all lowercase x vectors. We have a certain type of associativity as given in part 6. It's a kind of an exotic associativity. In one case, we're dealing with scalar multiplication on vectors, and in the other case, we're dealing with scalar products. So we're saying alpha times a vector beta x equals a scalar alpha beta times vector x. Again, over here, right between the scalar and the x, and that's your scalar multiplication. So here we've got scalar multiplication iterated with scalar multiplication. Strictly speaking, over here, there's no, on the surface of it, there's no multiplication of scalars over here. It's all scalars times vectors. On this side of the equation, there is. So it gets kind of a relationship between those ideas. Seventh, alpha plus beta, scalars alpha plus beta times x equals alpha x plus beta x, distribution of scalar multiplication over scalar addition. So it's an interaction between the two things we do, which is add vectors together and multiply by scalars, as relates to summations of the scalars. And similarly, in number 8, we get distribution of scalar multiplication over vector addition. Alpha times x plus y equals alpha x plus beta y. So 2 different versions of distribution there. We'll denote this linear space simply as x, though there's a lot of structure to it, all 8 of those properties, along with the fact that it has to come with a field of scalars. All right. These are called linear spaces because they involve linear combinations of elements of x, linear combinations of vectors. That is, we can add vectors together and multiply them by scalars. Those 2 things combined is what a linear combination is. As you know from your linear algebra experience, we'll formalize a little bit of this stuff later though. You may have noticed that the definition of linear space is the same as the definition of a vector space. Check out my linear algebra notes, hyperlink to those, and definition 3.1 of a vector space In linear algebra, it's defined over the scalar field of the reals, but other than that, it's the same thing we've done here. We're just using a more general field for scalars. Some examples then of linear spaces are Rn, Cn, Fn. You know by the so-called, as I call it, fundamental theorem of finite dimensional vector spaces, an n-dimensional vector space over the reals is isomorphic to Rn. In fact, more generally, an n-dimensional vector space over field F is isomorphic to Fn, where n is the dimension. So we can draw conclusions from that general result that Cn must be what you get when you have a vector space of dimension n and the scalars are complex. Rn, dimension n, scalars are real. So we've got a bit of a classification of finite dimensional vector spaces. And in some sense, I'd say this class, functional analysis, is really about infinite dimensional linear spaces, to use our terminology. You've kind of got finite dimensional vector spaces dealt with in sophomore linear algebra. A definition, or maybe even just a notation, if A and B are sets of vectors, alpha is a scalar, we'll define set of vectors A plus set of vectors B to be the set of all lowercase a plus lowercase b, lowercase a and lowercase b coming from the obvious place. And we can take a set of vectors A, multiply it by a scalar alpha, define that to be the set consisting of all alpha A, where lowercase a comes from set A. Probably something you didn't explicitly do in sophomore linear algebra, because you probably didn't do a great deal of stuff with sets. I mean, sets are unavoidable in linear algebra, but you didn't emphasize it, I suspect. If we take Y, a non-empty subset of X, where X is a linear space, if Y itself is a linear space, then Y is called a subspace of space X. You've dealt with this in sophomore linear algebra. Here comes some more definitions with which you're familiar. Given a set B in a linear space, a finite linear combination of elements of B is an element X, a vector, of the form X equals sum from I equals 1 to n, alpha sub I times B sub I, where the alpha sub I are scalars and the B sub I's are from this set B of vectors. The alphas are called the coefficients of the linear combination, and hey, that's what puts the linear in linear algebra, is linear combinations. So if we're talking linear spaces, it ain't surprising that we're encountering this stuff again. Now, we defined a subspace in this previous definition to be a subset, a non-empty subset, which is itself a vector space. Sorry, a linear space. So non-empty subset of a linear space, which is itself a linear space, is by definition a subspace. But in linear algebra, you probably dealt with subspaces, and you dealt with showing something's a subspace by showing, next note, we've got Y as a subspace if it's closed under vector addition and scalar multiplication. That's the two things you do in a linear space. You add vectors together and you multiply vectors by scalars. Combine those two things and you're getting what's called a linear combination. So we could just as easily have stated that non-empty set X, non-empty set Y, a subset of set X, where X is a linear space, is a subspace if Y is closed under vector addition and closed under scalar multiplication. And that you likely did in sophomore linear algebra. That was a test to see if you had the test for subspaces, actually is what it's called in my notes as reference there. Given a set B in a linear space, the span of B. So we're dealing with a set of vectors and defining the span, denoted in here, SPAN of B, is the set of all finite linear combinations of elements of B. This is the first time I've used this terminology, as if to imply there were such a thing as infinite linear combinations. There ain't in sophomore linear algebra. There ain't in the vector spaces you've likely been exposed to so far. That's one of the things we'll liberate you from. We'll deal with infinite linear combinations in here. So you know it's some kind of series thing in here. Ooh, if it's some kind of series thing, then I'm going to worry about convergence and divergence in here. Wasn't a topic in sophomore linear algebra. Isn't a topic in here just yet, but we'll need some equipment to deal with infinite linear combinations in vector spaces. Set B is a basis for linear space X if every element in X can be written uniquely as a finite linear combination of elements of B with non-zero coefficients. Okay, might be you had a different definition in mind for basis. More of that in a note or two. But here we're requiring a unique representation in terms of linear combinations. Possibly, and I'd actually recommend you carry this idea in your head, you think of a basis as a linearly independent spanning set. That's equivalent to what we've got here. Again, more of this at the bottom of this page, or more at this area. One more quick little definition though. A linear space is finite dimensional if it has a basis with a finite number of elements. Otherwise, it's an infinite dimensional vector space. And that's the ones in here that we're really interested in. Now, about this idea of a basis, so let's explore that a little bit more. I guess actually we'll deal with a linearly independent spanning set. Sorry, that looks like that's the next page. A little bit of commentary about bases at this stage. We can show in linear algebra, then in a finite dimensional linear space, all bases have the same number of elements. See a corollary called invariance of dimension for finitely generated spaces in my linear algebra notes. That's what allows you to define the dimension. It's the size of a basis. All bases are the same size. Dealing with a finite dimensional case, that common size is called the dimension of the space. In fact, in an infinite dimensional linear space, it can be shown that all bases have the same cardinality. All right, so we're going to be dealing with infinite sets. But as you know from your senior level analysis experience, there's different levels of infinity. There's different infinite cardinal numbers. But at least we're getting the same cardinality for all bases, even in the infinite dimensional case. We're going to modify these definitions a little bit in our study of infinite dimensional linear spaces to get a more tangible and a more geometric handle on the spaces we're dealing with. The best infinite dimensional spaces of all are Hilbert spaces. They have all the geometry of Rn, yet they're infinite dimensional. Details to follow. It's not really part of the definition of a vector space or a linear space, but it can be shown that every linear space actually has a basis. And nowhere in the definition, we had like 8 different properties. There's nothing in there about a basis. So turns out we can prove any vector space has a basis. It's an awkward proof. It requires the axiom of choice. Actually requires something equivalent to the axiom of choice. But anyhow, here's a link to some notes that establish that vector spaces actually have bases. What's particularly unfortunate about the proof as well, because it uses the axiom of choice or something equivalent to it, it's not constructive. It doesn't tell you how to find a basis. It merely tells you there's a basis out there. If we were going to do applied math, and a lot of applied math is done in infinite dimensional vector spaces, linear spaces, we need a basis. We need our hands on a basis. So as I said, there'll be a bunch of details to follow about how to deal with infinite dimensional linear spaces in a pragmatic way. A pragmatic way is a way that imitates the way Rn behaves, the vector spaces that you're most used to. Set B That'd be a set of vectors in a linear space, is said to be linearly independent if no element of B can be written as a finite linear combination of the others. All right, possibly a definition you encountered in terms of sophomore linear algebra, certainly concept that you should be familiar with from sophomore linear algebra, but maybe not quite the definition you had of linearly independent. So let's resolve that. Equivalent to this definition of B as a linearly independent set is that any finite linear combination of elements of B which yield a zero vector must only have zero coefficients. And probably not worded quite like that, but that's likely the definition of linearly independent set of vectors that you dealt with in sophomore linear algebra. Take a linear combination, set it equal to the zero vector. That implies all coefficients must be zero. And you certainly did this kind of thing early on in sophomore linear algebra, because you would set that linear combination up, it would lead to a system of equations, and then you'd use matrix methods to deal with that system of equations. Because you're setting that linear combination equal to the zero vector, it'd actually lead to a homogeneous system of equations, which you know has a solution. If that solution is unique, it must be all zeros, and that's how you showed linear independence in sophomore linear algebra. All right, I complained about this upstairs. This is a graduate level course, so we're assuming a higher level of maturity than sophomore linear algebra. And one thing we're getting here, and I really wouldn't mind doing it the old sophomore way, is notationally we're not distinguishing between scalars and vectors. Now, if there was a pattern, you may have noticed a pattern where we were using Greek letters for scalars and regular letters rather late in the alphabet to represent vectors, X, Y's, and Z's. That's what we've used so far. But we didn't draw any notational distinction between scalars and vectors. Now, the biggest place, and that's a problem, is when we're talking about zero, because there's both a zero scalar and a zero vector. And those are big time different things. That's a scalar. You can do certain things with scalars. That's a vector. You can do certain things with vectors. I can add this 0 to vector x, but I can't add this 0 to vector x because this 0 is a scalar. And notationally, there's no distinction. So you're going to have to be careful and base on the context, whether we're talking about vectors or scalars. They usually will make a blanket comment. It's clear from the context whether we're dealing with scalars here or vectors here, or some combination of, which usually leads to vectors. In linear algebra, probably you put a little arrow over the vector, or maybe you bold-faced, and those are common ways to indicate that we're dealing with, say, the zero vector instead of the zero scalar. And here, it's clear from the context. Yeah, I might argue with that. It's implied by the context. Maybe it isn't always that clear. I'll be very mindful of this and point out notationally whether we're dealing with vectors or scalars to make sure we're all on the same page. It is a bit of a step if from linear algebra you're so used to very clearly distinguishing vectors from scalars. Something I would highly encourage, in particular if you're tutoring linear algebra, you definitely want to do something notationally to distinguish vectors from scalars. In here, you're experienced and you'll be able to tell from the context. Well, we'll be careful. All right, and here's our comment about basis. We defined a basis. Just look back at that. I couldn't make this statement until I had some of the other definitions out here. We defined a basis in terms of every vector can be written uniquely as a linear combination. What you may have heard and what hopefully stuck in your head from sophomore linear algebra is that a basis is a linearly independent spanning set. That's equivalent to this. Let's explicitly say that. No need to go through proof because you do that kind of thing in sophomore linear algebra. We could have defined a basis of a linear space as a linearly independent spanning set. The notes I have on linear algebra out there, that is exactly the definition they take for basis in the vector space setting. You know what? They motivate, the source I go to, it's Fraley and Beauregard's linear algebra. When they first deal with vector spaces, they deal with a vector space, the example Rn, and they motivate with Rn more abstract things. And you know what? My favorite linear algebra book says a basis of a vector space Rn is exactly this. Every vector can be written uniquely as a linear combination of the basis vectors. And then they show that's equivalent to this. In the more abstract vector space setting, where we're not necessarily dealing with Rn, they take this as a definition. It doesn't matter, they're equivalent. I encourage you to think linearly independent spanning set. When you hear basis, think that. What can you do with vectors? Well, I can take linear combinations of them. So by saying you have a spanning set for a vector space, that means you got enough vectors in this set to generate the whole vector space through process of linear combinations. It's a spanning set. Saying it's linearly independent says you don't have too many of them. So to have a linearly independent spanning set, you've got enough vectors to span the set and no extra ones. The written uniquely idea yields the exact same properties, but I like this statement better. Think of it as there's enough vectors there, spanning set, and there's no extra ones, linearly independent. One final comment. We really want to think of vectors as functions in here. We're certainly motivated by Rn and little n tuples of real numbers to represent vectors and ideas of arrows and orthogonality, all that geometric stuff. In fact, we really want to preserve a lot of that. But in here, you really need to make a shift to think of vectors also as functions. Now, if you're lucky, those functions will carry with them maybe some kind of idea of magnitude and direction, the way a physics person would describe a vector. What a vector is an element of a vector space that satisfies those 8 properties that we stated before. If you're lucky, you can talk magnitude and direction. But there's certain vector spaces where there is no magnitude. There's no vector norm. And there's vector spaces where an idea of direction is totally lost as well. They're not nice vector spaces. I really want to keep those ideas of magnitude and direction, but really expand our base of knowledge to also include an idea of thinking of vectors as functions. Hopefully you were exposed to a little bit of that in sophomore linear algebra. Here's an example of a linear space. Take as of vectors all a cosine x plus b sine x, where a and b range over the real numbers. So you get yourself a bunch of functions here. These functions looks like generate x. If I was looking for a linearly independent spanning set, I bet you we could take cosine x and sine x as elements of a basis. It's certainly a spanning set. The question then becomes, are cosine x and sine x linearly independent functions? And they are, and that's straightforward to show. Are they orthogonal? Do we have an orthogonal basis here, or an orthonormal basis? Well, now that requires some knowledge about inner products, and we're not quite ready for that just yet. But these are all good questions to ask about this. But here's an example of, and I think you would buy this, a 2-dimensional real vector space. Hey, this vector space is isomorphic to R2. If it's 2-dimensional and it has real scalars, then I know it's isomorphic to R2. All two-dimensional real vector spaces are isomorphic to R2. All n-dimensional real vector spaces are isomorphic to Rn. And a similar result holds for arbitrary fields F, not just the reals or the complexes. But there's a little example of a linear space. We could probably set up some particular type of differential equation and get this as a solution space. So it's likely you've been exposed to these ideas before, maybe not with this linear space verbiage, and possibly not with this idea of a basis and all of that in some other settings such as differential equations. But it's there. These ideas fit in perfectly with that stuff. So that takes care of 1.2. We'll come back to 1.3. There's a handful of proofs in the next section, so we'll deal with that and concentrate still on these ideas of functions as vectors. That's vital to what we're doing in functional analysis. Have a nice day. I'll see you in section 1.3 shortly.